want to start with this visualization of, you can see this, cool, of the escape velocity of what velocity you need to reach to leave the gravitational well of a planet. So if a lot of you saw the OSIRIS-REx launch a few weeks ago, you saw a rocket leave the Earth at about 25,000 miles per hour. And so for different planets or different objects, you need to go at different speed to escape that object. So this depends on the mass of the thing and also how compact that thing is. So you can see the rocket leaving from Earth and compare that to, say, the rocket that's leaving from Jupiter. Jupiter has a lot more mass, so you need to reach a much higher velocity. That's about 134,000 miles per hour to leave Jupiter instead of the Earth. And so if you were to compare this then with the velocity you need to leave a black hole, you need to go faster than about 600 million miles per hour, or faster than the speed of light. So this is a problem because nothing can actually go faster than the speed of light, which means that nothing can leave a black hole, not even light, not anything. And this is the thing that really defines a black hole and makes it a unique object to study. This is a prediction from Einstein's theory of relativity, and we really like to study these things to see if they really happen, to use them as tests for general relativity. But the fact that light doesn't escape from them makes them hard to study, right? If no light is escaping from the thing, how do you actually observe it, right? You can study stars by the light they give off, or something like planets from reflected light, but no light will actually reflect off of a black hole, right? If you were to shine light at it, it would just get sucked in, and it wouldn't actually reflect back. So how do we actually observe these things? Well, I'm going to focus on a few ways of observing them, and I'm going to be focusing on how we observe supermassive black holes. So there's also black holes that are a few dozens of times the mass of the sun that we've seen evidence for in our own galaxy. That's boring. I don't care about a few dozens of the mass of the sun. I care about a few million to a few billion, to even a few trillion times the mass of the sun. So we call these supermassive black holes. And we think that there's one in the center of our own galaxy. So I'm going to try to show you real data as much as possible instead of visualizations. So here's an example of real data of the passive stars near the center of our own galaxy. And so you can see this is data from about 1995 to this year from a group at UCLA showing the orbits of stars in the center of our galaxy. And so you can see that these stars are getting flown around by something in the center that's not giving off any light and seems to have a ton of mass. You need to have a lot of mass to fling the stars around by that much. And so this is pretty good evidence that there's something very massive and very compact in the center of those stars. And so this is really awesome, but we can really only get this kind of data for our own galaxy. Maybe with new adaptive optic systems, we'll be able to do this for a handful of nearby galaxies. But really you need to go to other methods besides looking at the orbits of things around it to study other supermassive black holes. So the second method is definitely familiar to you if you were here last month to see Kevin Halen's talk, is you can look at what happens when the black hole interacts with interstellar gas. There ends up being a lot of gas and dust in between the stars of a galaxy. This gas is, we call it dense because it's denser than the vast emptiness between galaxies, but it's actually still much more diffuse than, say, the best vacuum we could create on Earth. But nevertheless, this gas, when it comes close to the black hole, something interesting happens. This gas will end up being pulled into orbits around the black hole if it gets close enough. And that gas will start to run into itself, losing some angular momentum and eventually falling into the black hole. We call this an accretion disk, and it ends up releasing a ton of light and a ton of energy back into the galaxy. So I've got a few images up here. Again, these are all real images. So the optical image is here. See, there's a normal galaxy, and there's some dust going across the center, blocking your view there. But then we look in the X-ray or the radio, we see these big lobes of bright material coming out. And so we think that's material that's being lofted up because of energy from that accretion disk. And so there's some really spectacular examples like this. And unfortunately, a lot of the time it's a little bit more subtle. And so then the method that I've been working on is instead of looking at what happens when gas interacts with the black hole, we look at what happens when stars interact with the black hole. So this is actually the artist's conception, not the real data. But the basic idea is this. If you have a star that gets close enough to the black hole, it can actually be torn apart by tidal forces. So what do we mean by tidal forces? Well, so we're familiar with tides on the Earth, right? We're familiar with the moon pulling on the water on the Earth. So what happens is that the moon is pulling a little bit more on the side of the Earth that it's closest to, a little bit less on the side of the moon that is farther away from. And so what this results in is kind of an oblong shape, where some of the water is being pulled a little bit more and some of it less. And that oblong shape rotates as the Earth spins, depending on where the moon is. So fortunately for us, the moon is not very massive, and the moon can't actually pull on the matter of the Earth very much. If that was instead a black hole, it could be enough to actually pull apart what's holding the Earth together. So for a star, what's happening is that if that star gets close enough that the tidal forces on one side of the star versus the other are stronger than the gravity actually holding the star together, it can rip apart that star. So this gets the fun name of spaghettification, and this cute gif of what would happen if we actually sent a space probe to a supermassive black hole. So this is even before you get to the event horizon or any of that crazy stuff. This is just a simulation or an artist's conception of what would happen if you put some space probe close enough to the black hole. It would just start getting stretched apart like that, assuming it's already on its way in. This GIF I find a lot less disturbing than the GIFs I found of astronauts in the same scenario. You should probably avoid that. It doesn't look, it looks kind of painful. So again, this is the artist's conception of what's going on. But what does this really look like to us as astronomers? Well, it's a little bit less dramatic, but here's a general idea of how we think we can find these kind of events of a star getting ripped apart by a black hole. So we have a picture of a galaxy, and there's groups like the Assassin Survey. Yes, it's called the Assassin Survey. The All-Sky Automated Search for Supernova, and they take a picture of a large number of galaxies every few nights. So they have this picture, and this is starting in July of 2014. They took another picture, subtracted it off, and there was no change. You just see some white noise here. So all through June and July, there's basically no change in the galaxy. And then at some point in November, you start to see that there's this dot showing up, where there's a new source of light in the center of that galaxy that wasn't there before. And so this tells you that there's something that went off in the middle of that galaxy. But just from this, you can't really tell, was it this kind of tidal destruction of a star, or was it a supernova or nova or any other number of things that can cause this kind of transient phenomena. So what they do is in these surveys, like Assassin, they see this, they say, oh, that's something, let's get a spectrum of it to see what it is. So what they do is they use another telescope and essentially take that light and put it through a prism to get a spectrum of it. So what that just means is they measure how much light they're getting from the object at different colors. So this is showing color from blue and purple into red and the infrared a little bit. And in black, this is a plot of the amount of light at different colors they got when they looked at this galaxy in 2007. So you see there's some features where it kind of dips, and it has an overall kind of shape like this. And then when they looked at it in late November of 2014, after they saw this bright thing go off in it, it looked like this in red. And so this looks very different. It has these big features here and here, and this feature can have to here, whatever's going on here. And so they know that something different is going on. And if you got this kind of data for supernova or this kind of tidal destruction event or nova or anything else, it will look different. This is basically giving you the fingerprint of the kind of thing you're looking at. It tells you the kind of elements that are in it, the pressure, the temperatures in those elements. You can get a lot of information from data like this. So by getting this kind of information, we're pretty sure that it was actually a star getting torn apart by the black hole. So what I work on, you can probably tell from the fact that this is from 2014 that this is kind of new. The first one of these objects that people were really certain that it was in fact a star being disrupted was only in 2011. And so this is still a pretty new field, and so you can ask pretty basic questions and get some interesting results. So we asked the question, what kind of galaxies do you find these kind of events in? So what galaxies host these events? So what do I mean by what kind of galaxies? What I really mean are what kinds of stars are in the galaxies that are hosting these events. And so just like I talked about the fingerprints of different kinds of events, we can look at the fingerprints of different kinds of stars. So this is showing what it would look like if you pass stars of various different types through a prism. So you can see a couple different effects here. These stars over here have more blue light, these have less blue light, they have more red light, these have less red light. And you can see these dark lines, so it's not the projector, those are actual characteristic lines that show up that can tell us something about the type of star. And so what's interesting about the way that these stars are displayed is that the stars up here, these bright blue stars, these are very short-lived stars. And these stars down here, these are longer-lived, dim red stars. And so if you can look at a galaxy, and if you see that it has these bright blue stars, these are young stars, and they have to be constantly replenished for you to see them. So if you look at a galaxy and you see bright blue stars, it has to be constantly making new stars, replenishing those blue stars, so that you are able to see them now. So if you said, say, form a bunch of stars all at once, you would form, some of each of these. And then if you just stop forming any new stars, eventually you would see these would die off, and then these would die off, and then these would die off, and then these would die off, and so on. And so if you look at the kind of stars that are in a galaxy, you can get a history of when the galaxy was forming stars. So if we look at pictures of real galaxies, we can kind of see this. If we look at spiral galaxies like our own Milky Way, or something like this, you see that this spiral galaxy has a lot of these bright blue stars, especially in the outsides, in these clumps. And then this galaxy over here, it really just has some red stars in it. And you don't see a ton of any blue stars. So we can say that this galaxy, it has most of its light coming from these bright blue stars. It's continuously forming new stars to replenish those bright blue ones. And this one over here, because only the red ones are left, it stopped forming stars a long time ago. So we call these red dead galaxies, and these star-forming galaxies. So that's kind of an intermediate step. If we want to look at galaxies that are maybe in between, we have to figure out how to identify these intermediate stars. So fortunately, there's a couple of features here. These two absorption lines are really characteristic of intermediate age stars. So we can look for galaxies that have a lot of intermediate age stars and use those as candidates for galaxies that are in between. So this galaxy right here, it has a lot of intermediate stars, but none of these young stars, and then it still has these red stars. So this galaxy has recently stopped forming stars, and we can infer that because we can see the kinds of stars that make up its light. So another way of looking at and comparing these galaxies is on a plot like this. I promise this is the only plot that's not a spectrum, and this will be dead soon. But so this is just plotting the young stars versus the intermediate stars. And all these black points are galaxies from the Sloan Digital Sky Survey. And so you can see these galaxies here, they have a lot of young stars and intermediate stars. And so we see that they're star-forming galaxies, they're forming stars now, and they have been over the time scale of these stars as well. And then we have our red dead galaxies, they don't have any young stars or any intermediate stars. And then we have galaxies here that are intermediate galaxies. So they don't have any of the new stars, but they haven't been long dead. They're just the recently dead galaxies. So our question was, what kind of galaxies host these events where a star is getting disrupted by a black hole? So you might think it's kind of weird to be comparing that question to this question, but it turns out that galaxies where that's happened actually prefer a kind of galactic history. These are the galaxies, right, there's only 8 of them, this is a young field, that we've observed this kind of event in. And a lot of them seem to be in these intermediate galaxies. There's almost none in the star-forming galaxies, and maybe only one in a red dead galaxy. But most of them are in these transitional galaxies. That's really weird, right? Like, this isn't because I skipped over something or like you got a new beer while I was explaining that. It's weird that the stars around the supermassive black hole should care about the global history of the galaxy. And so we wanted to figure out why this was the case. And so to do this, we wanted to, a natural place to look is to understand, okay, so if they're in transitioning galaxies, how do galaxies transition between types? And are there any clues from that process that could inform why more stars are being torn apart by the black hole? So one possible avenue for this transition is galaxy-galaxy mergers. And this actually happens quite frequently in the universe. I'm showing some examples of some different galaxy pairs that have been observed in different stages of a merger. So these kind of come together, collide, and end up in this remnant here. And so you might think this is a really rare occurrence. Space is mostly empty. Why should galaxies collide with one another? And so to do that, I actually have 2 trivia questions that kind of inform some intuition of how galaxies actually even get close enough to collide in the first place. So I've got 2 trivia questions. The first one would be if you have between like our sun and the next nearest sun, say, or typical distance between suns, how many suns would you fit in that distance? to make sense. So I'm basically asking, like, what's the distance between here and the next star in units of other suns, not in units of light years or parsecs or anything. How many suns could you fit between us and Atlas and Star? And then the next question will be the same, but for galaxies. So anyone want to hazard a guess for how many suns would fit between us and the next sun?
We'll take the closest answer.
Yeah, within a factor of like 10 or 100. Right? It doesn't have to be exact. 80? Yeah, 80? It's bigger. Yes. Smaller. You said 10 to the 11. It's not 10 to the 11. It's a little bit smaller. I'll take 10 to the 8. That's very close.
Congratulations.
Yeah, so that's quite a lot. I think it's more like 30 million. You're really close. Yeah. So you could fit, a very vast number of suns between us and the next sun. So stars are very unlikely to collide. So what about for galaxies? How many galaxies do you think you could fit between us and the next galaxy? Yeah, that's actually really close. Yeah. I think about 30 million between us and the next sun, and 10 to 100 between one galaxy and the next. And so galaxies are actually, even though space is mostly empty, they tend to cluster in groups and even dense clusters. And the separations between galaxies aren't that large. And it seems like most galaxies could in fact experience a merger sometime in their history to make this a pretty common process. So this one is my attempt at doing this to scale of a galaxy and then the next galaxy. They're not that far apart. You can imagine that if you were playing like darts with one, you wouldn't have to be very good at darts to hit the other galaxy with this one. For my estimated size of how big this will show up on the projector, you've got this star, and the next one is in London. So you'd have to be extremely good at darts to hit that with that. So we do in fact see examples like this in the real universe, things that look like what we think might happen if we sent two galaxies colliding into one another. And kind of a rogues gallery of cool looking things. So in our nice little corner of the universe in the Milky Way, do we have to worry about this? Like, do we have to worry about other galaxies colliding with us?
The Andromeda.
Yeah, we totally do, right? Andromeda is actually on a collision course with the Milky Way in about 4 billion years. So I wanted to show a simulation of what we think galaxy mergers look like. So this is an example of the Milky Way by some people, including Professor Bettina Bezla, who's out of U of A, of the Milky Way, and its companion Andromeda, and a simulation of what they think will happen over the next few billion years. So they're not that far apart on this thing, even in this weird view. We've got another billion years, and then
out of curiosity, by mass, which one's bigger? Which one's bigger?
Andromeda's a little bit bigger.
Is it?
It's still kind of up for debate. It's really hard to know mass of our own. Yeah, so they kind of do a close passage and come together eventually. And like right now, more stars will be torn apart by the supermassive black hole. So seeing the simulation, it sounds a little bit less crazy that maybe in all that chaos, you would end up with more stars that get close enough or on good enough orbits. And then you can see that eventually this galaxy, even though before we had two spiral disky galaxies that were blue, now we have one kind of blobby suborbital thing that's red. So this is a really good candidate for how galaxies might transition between these types. People like me working on estimates of how often this should happen, and it's maybe half of the time this should influence how a galaxy evolves, so it's pretty common. So if we look at galaxies that are in this transitional phase, are candidates for these guys, if they're plausibly post-merger. Here's some examples of galaxies that have no young stars, but a lot of intermediate stars, and they have all these big features. The top are some images from Hubble, and you can see all this flowing out material, and even in some of these other ones you see multiple galaxy components and material flowing out everywhere. So it seems like our transitioning galaxies could have had a recent merger. So there's a couple of explanations for why this might result in more stars getting torn apart by the black hole, and I'm going to skip these two at the bottom. Basically, if you have more stars or more gas in the center, that could do this. But the really exciting one is what happens if you have the two black holes in each of those merging galaxies, now in spiraling together. What we think can happen is if you have the two black holes, they'll spiral together just like the galaxies will, and through what we call three-body interactions. Basically, one of the black holes can slingshot stars into the other black hole. So I call that three-body interactions. And so I have a third trivia question. Basically, I don't know if any of you have read this book. It seems like the kind of crowd that might have. What's unique about the three-body problem when you have three gravitational masses interacting? Yeah.
Has it been solved yet?
It has not been solved yet. Yeah, so that's basically the answer. The three-body problem is unsolvable, and you can't write down an equation for how three different masses should interact because the gravity of the other two will inform how the third one moves, and same for any combination. And so you can really only solve this by doing numerical simulations. We can't write down an exact equation for these. So it ends up having some chaotic behavior. So I've got a video to illustrate this. It starts out really small and it zooms in, where there's two masses here, and a third thing is going to come in and show its trail in red. So it starts out so, and then, yeah, you can't write that down in an equation very easily. You need to solve this numerically. And so I think you get an impression where having the two black holes might help you send one into the other. So this simulation just showed what happened when you had three things that didn't have any extent. There's no tides or anything like that. So let's look at what happened when we add in tidal forces and we simulate as if those two things were the black holes and the other thing was a star. And it gets disrupted like right away. And then, so this is a simulation out of Colorado by Eric Cullen, who just put this out earlier this year. And so you see some really cool things, right? There's all these different streams. There's actually an accretion disk around both of these black holes. So if we saw this, we might see maybe two events. We think the light is coming from just that accretion energy, but you see a ton of other stuff happening here. There's streams that are crossing in on each other that might generate something that we can observe and see. And you end up with this kind of mass field of all this debris from the star, which could maybe have an impact on what's happening in the rest of the galaxy, if that happens often enough. Yeah, I think this is a really neat simulation of how that might happen. So, okay, so if we look at the actual host galaxies like I was talking about, they have intermediate stars, but did they actually have a recent merger? Well, we can just look at the pictures and see if they had evidence of material flung out, like those other images. But we have, oh, this is almost done, I think.
Can I get that as a screen save? That's awesome.
Yeah, all right, so we want to see if the actual galaxies seem like they've had a recent merger. And these are the only pictures that we have of these galaxies. These are all from Sloan. They were just archival images. And all of these things are pretty far away. And so, I mean, looking at this lobby thing, did that have a recent merger? I don't know. You couldn't really tell, given just the data that we have. If we had Hubble Space Telescope imaging, we could do way better. It's kind of before and after of a galaxy that my group got data from before. So this is a Sloan image, and this is the Hubble image. The resolution is just orders of magnitude better. You can see that this feature was there before, but like this feature down here, you can see that. And seeing these individual star clusters is useful, and you don't get that from the Sloan images. So in April, my group asked for Hubble images of those galaxies, and they said yes. So next year, we'll actually get images of those galaxies, as well as some of the data that we need to answer some of these other questions about those galaxies. So to kind of sum up, we want to be able to observe supermassive black holes, but this is hard because they don't emit any light. You can observe them by looking at the influence on the orbits of their stars, or gas, or stars that are falling into them. When we look at the galaxies that we observed a star get torn apart by a black hole, these seem to occur in grid galaxies that maybe had a recent merger themselves. And all this is going to be really important in the next 10 years or so when the Large Synoptic Survey Telescope comes online in 2023. You saw that I only had 8 of these things so far. It's going to find thousands of these things every year, 3 per night, which will be really exciting, and will quickly blow any of this analysis out of the water. But you have to find those 3 as a needle in a haystack of the 10 million other things that ALSA will discover every night. So the information like this will hopefully help us pick these out of the haystack to really study them in very detail, to actually use them to study the black holes like we wanted to in the first place. So I'll leave you with this cool visualization of what the sky would look like in the next 4 billion years as Andromeda collides with us. Thanks. Anyone have any questions? I can answer anything. I haven't seen Interstellar though, even though it was spoiled for me, so I can't answer questions about Interstellar. Yeah.
So there are a lot of globular clusters in our galaxy.
Yeah.
Could those be the remnants of mergers, past collisions with other galaxies?
So we don't think that the globular clusters are from those. It's actually still kind of uncertain how they form. But in our own Milky Way, we don't think that it's had a significant merger in the past, and it still has a lot of these. Definitely during the merger, more of these should form. And when we look at those merger remnants, a lot of those like bright blue things are in fact bright star clusters. So in other galaxies, yeah, that's definitely how some of them can form. Any other questions?
Okay, let's thank Decker again.